The Book of Why explores an underutilized science called causal inference, a tactic which mimics humanity's natural ability to determine a cause by observing an effect. By employing causal inference, scientists are able to mathematically determine the causes and effects of a given phenomenon. With the help of science journalist Dana McKenzie, renowned computer scientist Judea Pearl explains how he and his students at the University of California, Los Angeles, developed models and mathematical language that can point toward causation instead of just correlations. Even if researchers do not have data on all of the variables that might affect a given problem, they can use causal inference to create an informed estimate. By learning a mathematical language for causality, scientists will be able to prove cause and effect for complicated phenomena. They may even be able to devise theories without conducting experiments. Causal inference may also allow computer scientists and engineers to move one step closer to creating a machine that exhibits human intelligence. Scientists first developed causal inference in the late 19th century, around the same time that modern statistics came into being as a scientific discipline. Statisticians such as Francis Galton and Karl Pearson desired a method that could help them understand genetics and heredity. When Galton and Pearson failed to reason out a cause for these phenomena, they decided that science was incapable of fully determining cause and effect. Modern scientists who work in the field of statistics came to rely on data as the sole determiner of truth. Researchers in this school of thought believed that as long as scientists collected enough data and interpreted that data correctly, then they could answer any question that science might pose. Questions regarding causality based on inference and observation came to be considered unscientific and inherently biased. However, data by itself is insufficient when pursuing scientific truth. A data set can aid scientific progress, but it cannot tell a researcher if the question was posed in the wrong way or if the data was collected in such a way that it would skew the results of a study. One reason causal inference is so useful is because it resembles higher-level thinking. Humans are capable of 3 levels of thinking and reasoning. These levels are sometimes called the ladder of causation. The first level involves the ability to see and observe changes in a pattern and draw conclusions based on associations. Animals, as well as some machines programmed with artificial intelligence, demonstrate the ability to utilize first-level thinking. The second level is the ability to recognize factors that might interfere with or intervene in how a process usually functions, and to draw conclusions about how these interactions will affect the process. A caveman, for example, would have been able to use the second step of the ladder of causation to imagine what would happen if more tribe members accompanied him on a mammoth hunt. What sets modern humans apart from animals, early humans, and machines, however, is the third rung on the ladder of causation: the ability to reimagine how a past event might occur if something changed. Third-level thinking is characterized by the ability to retrospect and use imagination. In a court proceeding, a prosecutor can explain to a jury that a murdered man would still be alive if a suspect had not fired a gun. The ability to imagine alternate scenarios, or counterfactuals, is essential to humanity's ability to determine cause and effect. Imagining counterfactuals has played a crucial role in the development of civilization. Although there are many scenarios in which humans can intuitively determine cause and effect, humanity's innate causal reasoning skills are no match when faced with complex systems, like how weather systems work or how a medicine might affect a large population. If scientists want to be able to pose questions about why a phenomenon occurs the way it does, they need to embrace causal reasoning. To do that, scientists should utilize a common mathematical language that can prove causality. Thanks to advancements made during the latter half of the 20th century, researchers now have access to algebraic formulas that can aid causal inference. Although causal reasoning has not yet been widely adopted by the scientific community because data-based methods are still preferred, It may one day lead to scientific breakthroughs that statistics alone could never hope to accomplish. Key insights. 1. Scientists didn't find it necessary to develop a mathematical language that could prove cause and effect until they were faced with more complex questions in the 20th century. Some researchers argued that science can only determine correlations, not causation. 2. Popular statisticians derided the scientists who promoted causal theory, which pushed the method back decades. 3. Bayesian reasoning and probabilistic thinking moved scientists one step closer to causal inference. 4. Causal arguments allowed scientists to prove that smoking causes cancer. 5. The ability to scientifically determine cause and effect can help researchers prove the existence of human-made climate change. 6. Causal inference can be used to solve paradoxes that have puzzled statisticians for decades. 7. Researchers are unable to explain how deep learning machines complete complicated tasks because they are unable to communicate with machines using a common language. 8. Artificial intelligence will be incapable of human-like intelligence until scientists can teach computers how to use causal inference. Analysis. Key Insight 1. Scientists didn't find it necessary to develop a mathematical language that could prove cause and effect until they were faced with more complex questions in the 20th century. Some researchers argued that science can only determine correlations, not causation. Humans are adept at parsing the true cause behind simple cases of spurious correlation. For example, it's common for homicides and ice cream sales to increase during the summer, but few individuals would argue that selling ice cream leads to murder. Instead, an individual is likely to identify heat as the common factor. When faced with more complicated questions, scientists find it more difficult to distinguish cause from effect. Part of the reason causal inference has not been widely adopted is because it is regarded as less objective than data-based science. Scientists and the public tend to rate scientific methods that rely on quantitative data as more reliable and rigorous than those that rely on qualitative data. A social scientist who studies how individuals in a culture relate to each other, for example, is given less prestige than a chemist who studies how a medicine might interact with a patient. In a 2007 Scientific American article, author Michael Shermer argues that the so-called soft sciences, such as psychology and sociology, actually require more intellectual prowess than hard sciences like geology, because sociologists and psychologists are expected to build theoretical frameworks to explain how a phenomenon occurs. Sometimes these models are built in the absence of hard data. Shermer points out that even Charles Darwin believed that theoretical models are essential to scientific progress. After Darwin wrote On the Origin of Species, some critics claimed that his work was too theoretical, and that he should merely present his observations instead of drawing conclusions from those observations. However, Darwin countered that the idea of presenting data without a theoretical framework was nonsense. Without theory, scientists would only be left with observations and would never be able to draw conclusions about their data or delve deeper into a subject. Humans are natural storytellers and understand the world by framing their observations in a narrative fashion. By adopting causal inference as a scientific language, researchers will be able to tell a story about the data they have collected in a way that other scientists and the general public can understand. Key Insight 2. Popular statisticians derided the scientists who promoted causal theory, which pushed the method back decades. Ronald Fisher, whom many early statisticians regarded as a guru in the field, was a boisterous man who was quick to hold grudges against anyone who disagreed with him. Sewell Wright was among the many professionals he disliked. Wright, a geneticist, believed that evolutionary change could take place in sudden bursts, a theory Fisher vehemently contested. Wright also invented a method called path analysis that allowed scientists to use diagrams to determine cause and effect. Since Fisher disagreed with Wright on matters regarding both evolution and statistics, he mocked Wright's work, which pushed Wright's theories into obscurity because of Fisher's greater influence and authority in the field of statistics. Scientists may strive for objectivity, but they are still influenced by the same petty emotions as other humans. During the French Revolution, chemist Antoine Lavoisier was beheaded, ostensibly because he was part of the aristocracy. However, the true reason behind his execution was a personal grudge held by a competing scientist, Jean-Paul Marat. According to journalist Esther Inglis Arkell, Marat had promoted the idea that some animals and inanimate objects produced an energy which he said could explain occult concepts such as animal magnetism and hypnosis. Lavoisier considered the existence of such an occult energy preposterous and criticized Marat's occult theory publicly. Marat was so incensed that when the revolution began, he started a campaign to damage Lavoisier's professional and personal reputation. When Marat was killed during the revolution, his friends and admirers decided to continue targeting Lavoisier. He was eventually arrested and executed, among other political prisoners. Shortly after his death, the revolutionaries acknowledged that Lavoisier was executed because his reputation was smeared, not because he had committed any crime. Lavoisier was correct to debunk Marat's occult science and helped with other scientific advancements, such as identifying oxygen as a specific element. Nevertheless, Lavoisier likely would have lived to make other discoveries had Marat been able to cope with public criticism. Key Insight 3. Bayesian reasoning and probabilistic thinking moved scientists one step closer to causal inference. In the 18th century, Presbyterian minister Thomas Bayes created a philosophical argument which posited that an individual could determine probable outcomes of an event by taking already known information into consideration. This philosophy became known as Bayesian inference, a statistical process used to update a hypothesis with new information as it becomes available. Bayesian inference was later adapted into a mathematical formula known as Bayes' theorem, which could be used to determine probabilities. Bayes' theorem laid the groundwork for computer scientists to create Bayesian networks, which allow computers to use probabilities to improve their performance. Although Bayesian networks don't allow machines to determine cause and effect, they do allow computers to think in terms of degrees, rather than consider every problem from a black and white standpoint. Without Bayes' theorem, causal inference likely would have never developed. Bayes' theorem is a process forecasters use to predict the likelihood of an event occurring by using the information that's already known about the event to calculate probabilities. The theorem isn't just useful when applied to science. Everyday people can use the theorem to reason through personal conundrums and conflicts. In The Signal and the Noise: Why So Many Predictions Fail, But Some Don't, statistician Nate Silver argues that anyone can use Bayes' theorem to navigate uncertainty and mitigate extreme emotion, which can cause individuals to make rash decisions or come to conclusions that aren't supported by logic. For example, a business owner may suspect that an employee who has taken a sick day is lying about being ill. Before confronting the employee, the boss can employ Bayes' theorem. If the employee has been truthful in the past and has not abused sick days, then the probability that the employee is lying would not be very high. If the employee has been caught lying about illnesses or other things in the past, then the boss's suspicions might be bolstered by Bayes' theorem. Although Bayes' theorem can help scientists and non-scientists alike navigate quandaries, it's not foolproof. It relies not only on prior beliefs and information, but on the strength of an individual's convictions. Like causal inference, Bayes' theorem works best when the person using it is willing to revise his or her beliefs when presented with new evidence. Key Insight 4. Causal arguments allowed scientists to prove that smoking causes cancer. In the early 20th century, doctors started to see more patients who were suffering from lung cancer, a disease that was previously considered rare. During that same time period, cigarettes had risen in popularity. Scientists knew that cigarettes were statistically correlated with cancer, but were unable to prove medical causation for the illness. Some statisticians, like Ronald Fisher, argued the correlation was spurious. He believed that lung cancer sufferers likely had a gene that he called a smoking gene, which would make them crave cigarettes and would give them a heightened risk of developing lung cancer. That theory was debunked when Jerome Cornfield used a causal argument to show mathematically that Fisher's hypothetical smoking gene could not account for the rise in lung cancer. Causal inference allowed scientists to show that smoking was not just correlated with cancer, it was causing it. However, existence of a statistical correlation between smoking and cancer should be enough for governments to consider placing warning labels on products containing tobacco. Establishing a causal link between an action and a malady is especially crucial in medical science. Failure to recognize the cause of a sickness can have disastrous consequences. Doctors might not recognize the rise of a disease or might fail to mitigate it before it becomes an epidemic. The ongoing opioid epidemic that started in the 1990s, for example, came about because doctors believed that chronic pain patients could not become addicted to opiate-based pain pills. In Dreamland, the true tale of America's opiate epidemic, journalist Sam Quinones explains how a 1986 report, authored by Kathleen Foley and Russell Portnoy, was used by pharmaceutical company Purdue Pharma to convince physicians that its time-release opiates were safe for the general public. The idea that opiate-based medicine could be non-addictive flew in the face of common sense, and contradicted medical records showing that opium-based medicines led to addiction. Still, doctors wanted to believe that Purdue's medicine, OxyContin, was harmless because they wanted to alleviate their patients' suffering. Physicians started prescribing the pills for general types of pain, such as headaches and back pain, when the medicine should have been used only for patients with cancer and terminal illnesses. OxyContin became widespread, and users turned to heroin when they were unable to acquire pain pills. If scientists and doctors had used causal inference to test the claims made in Portnoy and Foley's paper, then the false belief that opiates could be non-addictive might not have spread so quickly. Doctors might have stuck with the correct assumption that opiates easily cause addiction and should be used sparingly in medicine. Key Insight 5. The ability to scientifically determine cause and effect can help researchers prove the existence of human-made climate change. Historically, scientists have been unable to attribute individual weather events to human-made climate change. Researchers presenting evidence of human involvement in global warming often couch their discoveries in terms of correlations and probabilities instead of causation. Since scientists are unable to state their convictions, many people are left with the impression that the existence of climate change is still up for debate. If more scientists use causal analysis to examine climate change, governments will be able to create informed policies that reflect humanity's best understanding of what causes extreme weather. Current scientific models present compelling evidence for climate change, but are better suited for predicting the weather than evaluating changes to climate over a long span of time. Causal theory has not yet been used to determine whether global warming is human-made or whether it is the result of natural variation in the environment. Since climate change is unlikely to impact an individual's life on a day-to-day basis, it's hard for non-scientists to understand the threat that global warming poses. A 2018 Gallup poll shows that more than half of Americans don't believe that climate change will affect them in their lifetimes. They instead believe that any disastrous consequences will be faced by future generations. Public perception of the threat is compounded by the fact that an individual's belief in climate change can likely be predicted by political affiliation. Only a third of Republicans believe that global warming is already affecting the planet. More than half of Republicans believe that any increase in global temperature is just a result of natural variation. In contrast, more than 80% of Democrats believe that the effects of climate change on the environment are already apparent. Since belief in climate change has become polarized along the political spectrum, it's difficult for politicians and party members to consider scientific evidence in an unbiased manner. When voters are not provided with a specific tactic for solving a problem, they tend to dismiss it or rationalize that it will be someone else's problem in the future. If the negative consequences of climate change are to be mitigated, scientists must find a way to speak with certainty about the immediate effects that climate change is having on the planet. Key Insight 6. Causal inference can be used to solve paradoxes that have puzzled statisticians for decades. Paradoxes are statements or problems that appear to have contradictory solutions. These contradictions occur when intuition suggests one solution to a problem, but a conflicting answer can be produced using probable logic. These disparate solutions exist on two different levels on the ladder of causation, which makes the true answer difficult or impossible to discern. Paradoxes sometimes offer fun brain teasers. They can also illuminate how human logic works. Using causal inference, researchers and scientists can navigate these paradoxes and more easily understand common logical errors. Since computers are presently unable to use imagination or causal inference, it's likely that even the most powerful machines in the realm of artificial intelligence would be unable to find a solution to a paradox. In fact, the idea that computers can't solve paradoxes is a long-standing trope in science fiction. One of the first instances of this trope appeared in Isaac Asimov's short story, Liar, which was published in the anthology I, Robot. In Asimov's story, a telepathic robot is tasked with answering any questions its operators put to it. However, because the robot has been programmed not to hurt humans, it lies when telling the truth would hurt the asker's feelings. The robot's lies end up hurting those who are asking questions anyway. When this paradox is described to the robot, it ceases to function correctly because it cannot determine a course of action that would allow it to not hurt people. Modern science fiction stories use the trope as a way to defeat evil machines imbued with artificial intelligence. For example, in the video game Portal 2, employees at the fictional science company Aperture are instructed to use paradoxes such as, "This statement is false," to disable rogue machines. While most humans are incapable of solving paradoxes outright, causal inference equations can be used to find results for statistical and probabilistic paradoxes. If researchers are able to teach machines how to use causal inference, it follows that those machines would finally be capable of solving paradoxes as well. Key Insight 7. Researchers are unable to explain how deep learning machines complete complicated tasks because they are unable to communicate with machines using a common language. In 2016, a deep learning program called AlphaGo became the first machine to beat a human champion at Go, a game that surpasses chess in its complexity. AlphaGo may have been able to beat even the most proficient Go players, but the developers of the program are unable to explain how the machine triumphed. Computer scientists rely on Bayesian networks and data to understand how deep learning machines work. If a deep learning machine comes up with a previously unforeseen answer to a problem, programmers are unable to ascertain how the machine reached that conclusion. If computers understood causal inference, there is a chance that programmers could ask deep learning devices how they reached their conclusions, which could give scientists better insight into cause and effect. Deep learning machines may not have the ability to think the same way that humans do, but they certainly can convince humans that they have this ability. In 1997, Russian chess grandmaster Garry Kasparov stormed out of a competition with IBM's chess program Deep Blue because he believed that the machine had superior intellectual abilities. Kasparov believed this because in his first match with Deep Blue, the machine made a move that Kasparov didn't predict. The move didn't result in the machine's victory, and in fact only delayed its defeat. But it still left Kasparov with the impression that the machine was imbued with superior causal reasoning. In fact, the machine had selected the move at random. Deep Blue's developers later admitted that the move was a software error they thought had been programmed out of its system. If Kasparov had continued playing his final game with Deep Blue, he likely would have ended the match in a tie instead of forfeiting. Despite the illusion of intelligence, Deep Blue couldn't actually think for itself. If a deep learning machine seems to be acting of its own accord, it's likely to be a software malfunction, not proof of strong artificial intelligence. Key Insight 8. Artificial intelligence will be incapable of human-like intelligence until scientists can teach computers how to use causal inference. Bayesian networks are tables or graphs that represent statistical probabilities and the conditions that are necessary to bring about those probabilities. These networks may have taught computers how to think in terms of probabilities, but machines still lack imagination. They are unable to consider alternate scenarios in which they achieve a different result. If computer scientists are able to teach machines how to use causal inference, then machines will become capable of imagining different worlds. Machines will be able to think like humans do, that is, in terms of cause and effect. Hypothetically, machines created through artificial intelligence may one day be able to distinguish between human notions of good and evil and exhibit free will. If machines are one day able to exhibit free will, then society may have to grapple with the idea of granting machines personhood or even citizenship status within countries. Humanity has long justified its superiority in the animal kingdom by touting its superior intellectual abilities. A robot with the ability to think like a human would essentially be indistinguishable from a human in many ways. Machines that are capable of blaming themselves or other machines for failure would likely be capable of feeling upset at the prospect of failure. These machines might become capable of exhibiting other emotions like jealousy, joy, anger, and love. If such machines are ever created, governments might have to debate whether human rights should be extended to machines. While science fiction writers often envision a world in which machines clash with humans, it's also possible that humans and machines may reach a point where they coexist peacefully as equals. Some machines may even develop romantic feelings for humans because the difference between machine and human is moot. While this potential future is presently fictional, as in the 2013 Spike Jonze film Her, it reveals the possibility that humans might find a way to treat intelligent machines as companions rather than as tools. Important people. Judea Pearl is an Israeli-American computer scientist and philosopher who promotes the use of causal inference in science rather than statistical methods that rely purely on data. In 2011, he won the Turing Award, which is given to people who significantly contribute to the field of computer science. Dana McKenzie is a mathematics and science journalist. His work frequently appears in Science Magazine, New Scientist Magazine, and Discover Magazine. Thomas Bayes, 1702 to 1761, was a minister and statistician who argued that a prediction becomes more accurate when a forecaster uses previously known information to predict probable outcomes. His philosophical argument was later used to create a mathematical formula known as Bayes' theorem. Francis Galton, 1822 to 1911, was a Victorian scientist and eugenicist who discovered a law of statistics known as regression toward mediocrity, which means that outliers tend to move toward the mean over time. For example, tall men tend to have sons who are still tall, but not as tall as their fathers. Carl Pearson, 1857 to 1936, was a mathematician and disciple of Francis Galton who believed that data, when correctly interpreted, was the only factor needed to conduct scientific analysis. He believed science could never prove causation, and that causation was really a specific form of correlation. Sewall Wright, 1889 to 1988, was a geneticist who created path diagrams and path analysis while studying how guinea pigs pass on fur color to their offspring. Path diagrams allow scientists to use data about correlations to compute causations. Likewise, if scientists have data about an effect, they can compute potential correlations or causations using that data. Ronald Aylmer Fisher, 1890 to 1962, was a renowned English statistician who was prone to personal grudges. He believed that it was impossible to scientifically determine cause and favored data-driven statistics as a result. Jerome Kornfield, 1912 to 1979, was an American statistician who challenged Ronald Fisher's belief that a smoking gene was the primary factor behind lung cancer. His argument became known as Kornfield's inequality and strengthened the theory that cigarettes were behind the increase in lung disease. Alan Turing, 1912 to 1954, was an English computer scientist who proposed that a scientist could determine whether a computer had human-like intelligence if an individual chatting with the machine couldn't tell whether it was a human or a computer. Turing's theory became known as the Turing test. Donald Rubin is a Harvard University statistician who helped introduce a language that researchers can use to pose causal questions about the data or subject they are examining. Author style. In the Book of Why, Judea Pearl emphasizes that the reason many scientists have failed to embrace causal inference is because they lack a way to explain the process in scientific terms. Likewise, Pearl and Dana McKenzie seem to struggle with consistently explaining causal inference in a way that is easily grasped by a broad audience. The Book of Why includes interesting and compact information about the history of statistics, but it also contains entire chapters devoted to mathematical formulas that are unlikely to be familiar to the average reader. Pearl often indulges in complex sentences replete with algebraic variables and phrases. These passages can be hard to follow for those who are not intimately familiar with common principles in math and statistics. Thankfully, Pearl and McKenzie offer multiple examples, including illustrations and models that can aid comprehension. As an Israeli native, Pearl attended a school where reading the Hebrew Bible was an educational requirement. The biblical stories clearly had an impact on Pearl, who begins several portions of the book with one of them. For example, he uses the story in which Abraham asks God how many righteous men would need to exist in order for Sodom and Gomorrah to be spared to demonstrate the threshold effect. Pearl does not seem to put personal stock in the veracity of biblical stories, but he finds them useful as a way to explain cause and effect. In addition to providing visual models for the reader, Pearl includes several paradoxes and brain teasers that the reader can solve using the methods outlined in his book. The Book of Why includes 10 chapters, as well as an introduction. Author's perspective. Since its creation, statistics has considered data a goldmine that can be used to discern the truth about a given subject. However, Judea Pearl believes that statisticians and other scientists are wrong to place so much blind faith in data. Pearl argues that data is inherently unintelligent. Scientists can use data to procure an answer to a question, but if their question is phrased the wrong way, the data won't point out their mistake. For Pearl, the Book of Why is a manifesto in defense of causal inference, which he believes will prove to be the key to rapid scientific advancement in decades to come. Pearl argues that so far the scientific community and society at large have not adopted causal modeling and causal inference. Consequently, much of science's potential has not been realized. Pearl is particularly hopeful about the effects that causal inference could have on the field of computer science. While machines don't currently have the ability to learn cause and effect, Pearl believes that the development of causal inference might one day lead to human-like intelligence in machines. He even argues that causal inference might lead to free will in machines. Humans will know that machines have human-like intelligence when they blame themselves or others for mistakes without prompt. For example, a robot with free will might blame another robot for failing to hit a home run if it loses a game of baseball. Although Pearl has made many personal contributions to causal inference, he is quick to give credit to all the other scientists who have advanced the theory. He references the work of his students throughout the book and singles out a few whose work has been significant to the development of the new science. By giving credit to his students, contemporaries, and forerunners, Pearl indirectly makes the point that scientific advancement can rarely be credited to one person.